Hi everyone, my name is Anand Samajdar. Welcome to this video presentation of our paper called AIrchitect. Custom architecture design is a capital and time intensive process. However, it is also a data-driven decision-making task, which makes it an ideal candidate for automation using machine learning. Ideally, we would like to build a model which can learn to predict the optimal architecture and workload mapping parameters when queried with design objectives and constraints. However, designing such a solution requires us to answer a few key questions, like whether there exists any learnable pattern in the task. What should be the optimal data space suitable for any learning algorithm to work? What is even the best way to formulate the problem for a model to learn? Or is there any solution which is generalizable? In this work, we try to explore the answer to these questions using 3 case studies. In the first case study, we try to learn the sizing of a systolic array of MAC units in rows and columns when provided with parameters of a GEM workload and max compute capacity. In the second case study, we examine the proper buffer sizing allocation for a systolic array. And the third case study examines the optimization space when mapping concurrent GEM computations on differently sized MAC arrays in order to achieve maximum performance and energy efficiency. In this talk, I will be talking about 3 major sections. First is analyzing the design space for learnable patterns. Next, I will talk about formulating our problem domain into a ML problem. And then I will share our results on learning the optimization spaces of our case studies. Let us dive into the exploration of learnable patterns. Let's consider the first case study. In this case, we construct a design space such that when queried with matrix dimensions of GEM workloads and maximum allowable MAC units, we obtain a set of optimal row and columns of the array and the optimal data flow. To keep the space bounded, we allow the MAC unit to be in powers of 2 and look at the array dimensions which are powers of 2 as well. We try to examine the cost landscape to see if there is any pattern of the optimal shape for various data flow for a given GEM and MAC units. We see that optimal configuration changes for the various data flows. When an additional parameter like maximum MAC unit is changed, the relative shape changes as well. Moreover, proxies such as array utilization are of little help to predict the optimal array shape. We conduct another set of experiments to see if there is any correlation between the optimal array shape and maximum MAC units. We notice that for a given workload and a given data flow, there emerges a hint of a pattern. However, this pattern is not consistent across data flows. Moreover, even for the same data flow, when the GEM workload changes, the pattern kind of disappears. This indicates that we have to investigate even higher dimensional models. Consider this chart of optimal array dimensions for 512 MAC units with output stationary data flow. We plot the distribution of the optimal array shapes for 10,000 workloads as circles, where the size of the circle depicts the relative frequency at which the given shape is optimal. We plot similar distributions for weight and input stationary data flows. When the charts for the 3 data flows are superimposed and the maximum array size is varied, an interesting pattern emerges. In the first glance, we observe that there are a few configurations which are more optimal than others. These configurations correspond to almost square-like shapes. However, we see that all the configurations are optimal for at least one workload. Interestingly, the most favorable configuration is not the square one, but the one with 2 times as many columns as rows. Unfortunately, however, we cannot determine the optimal data flow from this space. So the natural question is, can we find similar patterns to predict the optimal data flow? In this chart, we plot the optimal data flows in the space of optimal array shape in the y-axis and the shape of the input operand in the x-axis. We can now see that in this particular space, the output and the weight stationary data flows can be clearly separated. Still, it is difficult to distinguish if the input stationary data flow is optimal over the other data flow. This separation can be seen when we construct a similar plot with the shape of the weight and the output matrices. In the first plot, there is a clear separation between input stationary and output stationary data flow, while in the second plot, there is a clear separation between input stationary and weight stationary data flow. We see similar distinguishable patterns for the second case study, where we optimize for the buffer size, and also for the third case study, where we compute the optimal mapping. Therefore, we see that there are clear learnable patterns present in all the cases. Now that we have evidence that the architecture and mapping space show learnable patterns, we examine ways to pose this optimization task as an ML problem. The decision boundaries that we have observed in the previous slides indicate that our task will be a good fit for classification or recommendation model. This table compares the two approaches. Both the approaches have existing models and literature. However, in the case of classification approach, we need one model per optimization parameter, which means for each feature in the output space, we would need to build and train a distinct model. In the recommendation model setting, we can create a unified output space for all the parameters, which helps us avoid redundancy in the model. Therefore, we choose to go with a recommendation model in this work. This slide shows the input spaces for the case studies. For the first case study, we have 4 features, which are the 3 dimensions of the gem matrix and 1 constraint for the MAC units. Similarly, the second case study has 8, and the third case study has 12 dimensions in the input space. The output space is captured as a set of configurations indexed by IDs. The objective of the model is to predict the ID corresponding to the optimal configuration when queried with the workloads and design objectives. We search using simulation to generate the datasets to learn the optimization space. Here we show the example of the first case study. To generate each data point in the dataset, we sample an exponent of 2 from a uniform distribution of integers to determine the maximum MAC units. And we sample 3 integers m, n, and k dimensions of the gem workloads from the distribution of dimensions in layers of popular neural networks as shown in the chart. Finally, for each point in the input space, we determine the optimal configuration by simulation. In our case, we use ScaleSim as the cost model. The figure on this slide shows the distribution of the optimal configurations in the output space of case study 1 for 5 million points. We observe that the distribution is not uniform, therefore a higher dimensional model is required. We intentionally do not normalize the dataset to ensure that no external bias is added. This brings us to AIrchitect, a custom recommendation model to learn the design spaces. The model is constructed by adding a feature embedding layer with MLP classifier. The output layer is a softmax predicting the optimal configuration ID. The input of the model is equal to the feature size of the input space. We train the model with Adam optimizer and categorical cross entropy loss function. We use a minibatch size of 32 and a train validation split of 80-10-10. With this model in place, we now evaluate its performance on learning the design and mapping spaces. For the first case study, when training on a dataset of 4.5 million data points, we observe that the model converges to a high validation accuracy of 94%. It takes about 11 epochs to reach the convergence, which is about 1 hour on our NVIDIA desktop GPU. When we look at the performance on the test set, we find that the test accuracy is close to the validation accuracy. And we find that the distribution of the predicted label closely matches the distribution of the dataset labels. I would encourage you to please refer to our paper for results on the other 2 datasets. In the study, we have also trained some off-the-shelf models on the datasets for all the 3 of our case studies. We have found that AIrchitect performs better than off-the-shelf models for all the cases. This makes it robust across the tasks. When comparing with a similar sized MLP model, AIrchitect seems to work better due to the embedding layers. Further examination of contributions of each layer type for the accuracy is one of our future works. This brings me to the conclusion of this video. In conclusion, in this work, we have observed that we can find learnable patterns in architecture and mapping space. Recommendation models like AIrchitect can learn and generalize the space with reasonable degree of accuracy. This opens the space for further research in automating architecture design and mapping using learning techniques. Thank you very much for watching the video, and I hope to see you in person in Date and have many interesting discussions. Thank you very much and take care.